talking about ratio in general. We've mentioned that we can use ratios to compare things and look at how things might scale up or scale down. For example, I've been playing around with the computer and taken one diagram and mushed it around a little bit. And suppose what determines what's a sedan, a sports car, or, well, it's a kind of a weird-looking van, but you get the general idea. If I compare the height to the length, I see that it's different for each of those three cases. And the comparison of height to length is one example of a ratio, and it determines whether you're going to have a sedan, a sports car, or some weird-looking little van kind of thing. Let's look at a more formal expression of ratio. First of all, as we indicated, it's a means of comparing different things, and notice that we say here it uses the fractional form, A over B. The quotient of two quantities, remember that we've said A over B really means A divided by B, and it's a relationship. It's two quantities that we want to compare for our own reasons. 3/4 might be a ratio between the height to the length, for example, of that little car that I showed you. It's expressed as A over B. We can look here at a particular example. There's an oval, and inside that oval we have more or less randomly scattered X's and O's. When we count these, we find we have 14 X's and 7 O's. We can say that the ratio of X's to O's can be written as 14 over 7. And since you're writing it as a fraction A over B, you always try to reduce things to the lowest terms, and that would make the information easier to understand. For example, if I told you there are 2 X's for every O, you can see that much more clearly in the ratio 2 X's to 1 O than you could in 14 to 7, although that carries information as well. There are some famous ratios that we could take a look at. Needless to say, our candy machine had M&Ms in it. So I thought that it would be useful to check this ratio out. So I bought myself a little bag of M&Ms, and let's take a look at expressing some of these ratios. Now, this may not actually be good because there's only a, it's not going to be characteristic. It's not going to be statistical. I really need to measure hundreds and hundreds of M&Ms. But let's just play with the idea of ratio with what I've poured out of the bag. Also, before the class, a number of us have been hitting on these M&Ms. They're hard to resist. But let's see what kind of ratios we might say we have here between the different colors. So I'm sorting them into colors. And this is not necessarily characteristic of M&Ms as a whole, just what we pulled out of the bag right now. If I look at ratios, I could say there's a ratio of 1 yellow to 5 greens, or a ratio of 5 greens to 6 blues. That ratio would be 5 greens to 6 blues, or 6 to 6 blues to reds. The ratio between orange and red would be 3 to 6, or 1 orange for every 2 reds. So M&Ms are, a good example of being able to express ratios. And in fact, I've heard that the M&M company keeps that ratio a secret. But of course, if you want to buy a few hundred M&Ms, you can figure out that ratio yourself. And they've probably done a lot of market research to get that ratio as pleasant as possible according to who knows what. Okay, so much for M&Ms. Another place where ratios are incredibly useful is in music, and in particular tuning musical instruments. And I brought my violin, if you pardon my misuse of the word, and when you tune the strings of the violin, they're tuned in certain ratios. And we talk about the frequency of the violin. Each string vibrates so many times a second. And when you listen to a violin, for example, I'm playing the E, the highest note, and here's the A, a little bit lower. What makes it sound nice is the fact that there are certain ratios to the strings. If I compare the A to the E and then simplify, I find those strings vibrate in the ratio of 2 to 3. And in fact, if I look at any of the adjacent strings, I find that ratio exists between each two pairs of strings. And musicians say that it's tuned in fifths. Every 5 notes of a piano is the ratio of vibration of the strings of 2 to 3. And when things are tuned right, and the player knows what he or she is doing, and in this case you can say or not, I do. I won't go any further because I've gotten this far without making a mistake and I know when to quit. Incidentally, if you're wondering what that little bit of the tune was from, it was from a tune called Southwind. Another use for ratio deals with simple machines, things like levers, gears, pulleys, ramps, and so forth. And it turns out that tools are simple machines. For example, here is a vice grip. And we can talk about the mechanical advantage of the machine, which is the force out, how much effort I can get out of this thing for how much goes in. So, for example, if I squeeze on this, how much does my finger get mushed for how much effort do I apply here to the handle? Because of various laws of physics, the energy in equals the energy out. If you take a tape measure and measure the ratio between how much you move, for example, how much motion you put in here, over how much comes out, you can determine what the total multiplication of force or mechanical advantage is. So this moves about 1 inch when this moves 4 inches. That ratio would be 4 to 1. So if I apply 1 pound of force here, I'll get 4 pounds of force here. Other tools work exactly the same way by giving you that mechanical advantage. For example, I have a screwdriver here. And if you think about the way the screwdriver works, if you look at how far you go around, think about the circumference as you make one rotation, you go around here a tiny amount, but then you go around the top a much larger distance. The distance you go around the top over the distance the screwdriver turns gives you some idea of the mechanical advantage of the screwdriver. And again, we have another ratio. Let's look at some others. Television screens, for example, give me another standard ratio. If you look at the width of a television screen versus the height of a television screen, every television in the United States, well, almost every television, I'm ignoring the really new widescreen stuff, all of the standard televisions have that ratio of, let's simplify it, 4 to 3. It's a standard ratio. If you have a television screen, measure it this way, measure it this way, do some math to simplify it, get in the lowest terms, and you'll see the ratio of the length to the height of a television is 4 to 3. Ratios also occur in art. It turns out there's a ratio called the golden mean, which they find is very aesthetic. You find this ratio in architecture and in art. It's 1.618 to 1. If we look at how this picture is framed, we see that the principal characters are included in a box having that ratio. We've looked at this ratio. What's the ratio of the circumference of a circle to its diameter? Do you know what that is? That's pi, our magic number 3.14159, and it goes on and on and on. Of course, we've talked about that. Let's look at some other practical problems where we're also dealing with ratios. A family earning $21,400 a year spends about $5,000 per year on food. We can ask, what's the ratio of the food expenses to the yearly income? We put that as A over B as a fraction, and then we try to simplify this a little bit, reduce it to lowest terms. Right away I see there's a factor of 100 in the numerator and denominator that I can effectively divide out, and I find that when I reduce this to lowest terms, I can express that as 25 to 107. For every $25 spent on food, there is $107 of income. And if I round that 107 off to about 100, we can say that this family spends about 1/4 of their income on food. For every $4 that come in to the family, $1 is spent on food. Here's another interesting ratio. Of the 365 days in each year, we find it takes 107 days of work on the average to pay for taxes. What's the ratio of the days you've worked for taxes to the total number of days? We find that you work 107 days out of every 365 days to pay your taxes, or you work about 1/3 of the year just to pay your taxes. Interesting statistic. Often, rather than using it as leaving ratios as 107 to 365, it pays to convert it to something called a unit ratio. I'll explain what that means. For example, if we have a group where we have 3 men for every 4 women, we can ask, how many men do we have for each 1 woman? If we reduce it that way, that's called a unit ratio. We take whatever the ratio is as a fraction and see if we can figure out what it is compared to 1. How do we convert to a unit ratio? We work to change that fractional ratio to a decimal. For example, we know that 3/4, if I divide 3 by 4, I get 0.75. I take the ratio, make it into a decimal. Then when I do, 3 men to 4 women is equivalent to 0.75, or 3/4 of a man for every woman. I won't go any further with this other than to use it as a mathematical example. Just wanted to show you, and I didn't talk about the situation. But we can say that we can now talk about how many men we have to 1 woman. That type of a calculation is called a unit ratio. Here's the reverse. We can also talk about it the other way if we want to. How many women do we have per man? And in this case, I would divide 4 by 3, and when I do, I would get about 1.33 women for every man. And again, it's a unit ratio because I've reduced it from how many women per 3 men to how many women per 1 man. And again, you can express this as 4/3 of a woman per man. You could say it that way, or 1.33 women per man. Either way works fine. Typically, when you do a unit ratio, you change one of the numbers to a decimal. And so the more standard way of expressing the unit ratio would be there's 1.33 women to every man in this particular case. Here are some other things that we can look at, and this information comes from the Pima Community College Institutional Profile for 2001. And I was just looking these things up. For example, what's the ratio of the income the college receives from property taxes to the income from tuition fees? When I looked at that, I found that was $47,553,000 from property taxes for every $25,424,000 from tuition fees. When I worked this out as a unit ratio by dividing the 47 million figure by the 25 million figure, I found out that we get $1.87 from property taxes for every dollar we get from tuition. Here's another example, one that, of course, I'm always interested in. What's the ratio of faculty salaries to administrative salaries? I looked this up, and I find that the faculty are paid about 23 million some odd dollars a year, and administrators are paid about $4 million a year. Dividing the 23,220,000 by the 3,950,000 to get the unit ratio, I find that $5.88, are received by faculty for every $1 that is received by an administrator. So the ratio of money paid to faculty to the money paid to the administrators, about 6 to 1, $6 for every $1. One more. We looked at the student body profile, and we found out that 28% of Pima College students are Hispanic and 4% are African American. What's the ratio there? It's 28 to 4, or we can again divide 28% by 4% and say that there are 7 Hispanic students for every African American students. Let's change tack a little bit now and look at calculating rates. First of all, we need to talk about what a rate is. A rate is a unit ratio that compares two different things. Remember, up to this point, we've been comparing the same things: blue M&Ms to green M&Ms. Money faculty receive for money administrators receive. Now we're going to change tack a little bit and talk about the idea of rate. Rate compares two different kinds of things. For example, miles per hour. Or for example, if I'm going to England, it might compare how many pounds you get of English money for every dollar. Speed is one of the most common rates that we talk about. It's the distance you travel over the time it takes you to go there. For example, if I go 183 miles in 3.1 hours, that's my speed, but we use a unit ratio. We actually divide that, and I find I go 59 miles roughly per every 1 hour I travel. Another common rate people talk about a lot is your pay rate. For example here, Jane receives $1,280 in her paycheck, which she gets every 2 weeks. We'd like to know her hourly rate of pay here. And so she works 40 hours in 1 week, so she would work 80 hours in 2 weeks. So we could say that her rate of pay for every 2 weeks is $1,280 per 80 hours. Then if we divide 1,280 by 80, we find out that her hourly rate of pay is $16 per hour. We can use this same idea to talk about unit pricing, and when you go shopping, this is a very useful tool for you to know whether or not you're getting a value for your money. And the unit price is the cost per 1 unit of the product, and that could include the cost per pound. if you're buying something that you measure in pounds. For example, if you have flour that's measured in pounds, cost per ounce, how many ounces of M&Ms did I have there? The cost each if I have a can of soda. The cost per length, so on and so forth, where you're relating the cost to some physical quantity of the unit itself. Here's an example. We could have different sizes or different brands that we want to compare, different prices, and often it's hard to know. For example, I went into one of the grocery stores and looked at a box of Cheerios, Honey Nut Cheerios, and it was $5.19 for 40 ounces. Then I looked at a box of the store brand generic product, and I just called it Honey Ozies, who knows what it was called, and I found it was $3.49 for 32 ounces. The question is, these are odd prices at odd physical quantities, so I need to know which to buy. And the way you can deal with that is find the rate, the cost per 1 ounce, find the unit price. If I take $5.19 and divide that by 40, that will give me the price per 1 ounce. When I did that, I find out the Honey Nut Cheerios cost me 13 cents per ounce, and when I do it with the generic cereal, I find it costs only 11 cents per ounce. So, surprise, surprise, it costs you less to eat generic stuff than it does the name brand. And of course, the only question you have to ask is it worth it? Are the Cheerios so much better than the Honey Ozies that you're willing to pay the premium to have honest-to-God Cheerios? Let's look at another couple of examples. Here we compared, in this case, we compared two different brands of equivalent things, of roughly the same things. Now let's look at comparing something else. We have two different sizes of apple juice, and we'll take generic apple juice. We have a large generic apple juice that sells for $3.99 for 128 ounces. And when we do the math there, we find the large juice costs 3.12 cents per ounce. Then we do the same thing for a small juice, the same brand. And we find that when we take the unit price, when we divide $2.19 by 64 ounces, we find that that works out to $3.42 per ounce. We see that, generally speaking, there's an economy of scale. The larger amount you buy of the same product, the better deal you get. But you can't be guaranteed that. It's not always true. So it's important when you go to a grocery store, if they don't list unit prices, and many do now, that you bring a calculator with you and do this comparison by yourself just to make sure that the grocery store is being upfront with you. Another interesting use of ratios is to talk about probabilities. Suppose, for example, I flip a coin. You know, we have heads and tails. And if I flip it and go like this, what are the chances of it coming up heads? Well, since we have two choices, heads and tails, we'll assume that it's not going to stand on its edge or anything. We have one, it can either be heads or tails, so the probability of this falling off my hand, who knows what, but the probability of it coming up either heads or tails is one chance in two possibilities. You see, we can express that as a ratio, 1/2, and that describes what's called the theoretical possibility or theoretical probability, because if there are two possibilities, heads or tails, and they're equally likely, and I flip it one time, there's one chance in two possibilities that I'll be right, so my probability is 1 in 2 or 1/2 that it'll be either one or the other. We could also look at whatever the favorable outcomes are, what we want, compared to all the possible outcomes. For example, if I have two coins, what are the possibilities? I can have two heads come up, a head and a tail and a head, or two tails. What are my chances of getting, as I flip the coin, one head coming up and one tail, the two coins at once? I see that there are two distinct probabilities. One coin comes up heads, the other tails, or oppositely. The chances are 1/2 of getting one head and one tail if I flip two coins. What about the chances of getting two heads? When I see there are 4 distinct possibilities, the chances of getting two heads then are 1 in 4, or I say that there's a 1 in 4 chance. Where we talk about probabilities a lot is the lottery. I saw this bumper sticker, the lottery, a tax on people who don't know math. Here's why. With Arizona Powerball, you pick 5 numbers, 1 to 49 each, plus the Powerball number, which is 1 to 42. It turns out that when you calculate the probability of your picking 5 particular numbers, 1 to 49, and the Powerball number, the probability, that ratio, is 1 chance in over 80 million. Here's how you can put that in perspective. If you purchase 50 lottery tickets every week, you will probably have a good chance of hitting the jackpot once every 10,000 years.